All right, so in this case, we're going to look at a minimization problem. And in this case, unlike the last case, we're going to have to consider multiple inequalities, not just a single inequality relating the two allowable changes. And this is because our solution will actually sit on as a corner of two of the edges of our feasible region that do not correspond to the horizontal or vertical axis. Remember, in the last problem we had two constraints, but one of them ended up not being relevant to the feasible set, so it was redundant. So we only had one. In this case, we'll have two. So in this case, we can think of a chemical mixture. X is representing the number of ounces of chemical A to be put into a mixture, and Y is the number of ounces of chemical B to be put into a mixture. There's a cost to creating such a mixture, so there's $25 per ounce, or 25 cents, whatever you want to, however you want to think about it. Let's just make it dollars. It's not really relevant to what we're talking about. For each ounce of chemical A, and $30 per ounce or 30 cents per ounce, whatever you want to think of, for each ounce of chemical B. So what could this be? The company could be, for example, disposing of waste chemicals. And depending on what those chemicals are, some chemicals are more dangerous to handle, and therefore the disposal cost is greater. Um, and sometimes you can mix chemicals that will actually decrease the volatility of the chemicals and therefore possibly decrease the amount of money it would cost to dispose of them. So we could think of this as a case where the company has multiple chemicals that are kind of waste chemicals, and it's okay to mix some of them, and it actually maybe makes a mixture might make them cheaper to get rid of than if we got rid of each one individually. So that's where these requirements may come into play. So we just want to solve the problem, and the company wants to know, okay, what is our solution of an optimal mix to minimize our cost? And then we want to know if these numbers in our cost function, 25 and 30, were to change over time, would we have to refigure out a new solution, or would we likely be able to maintain producing the same mixture ratio for an extended period of time? Again, why does the company want to know that? If they know that making a certain mixture will maintain its minimizing cost feature, then for a long period of time, then the company will go ahead and automate a procedure to create such a mixture. That'll make things more efficient, and it'll maybe reduce other costs the company may incur, as far as they might not. If you automate things, you don't have to hire as many employees to do things, so you can save money other ways that way. But if your model is going to be very sensitive to such a mixture, you're not going to want to automate the procedure, because then in maybe a month you're going to have to re-automate everything to do some new decision, and that can be costly on its own. So this is the general idea of sensitivity analysis: is you kind of want to forecast how long will a certain kind of decision be optimal, so that you can look at possibly automating a procedure and then saving money from a different point of view. So let's look at the graphical solution. So again, this is a minimization problem. Our inequalities were of the kind of greater than or equal to variety, so our feasible region is unbounded. It kind of continues on vertically and to the right indefinitely. But it has four edges, one edge on the vertical axis, one on the horizontal axis, and then each of those constraints that we had in our model gives us one of these other two edges. Now what we can see by solving graphically is the minimum cost is going to be $195, and that's tied to a decision of mixing 3 ounces of chemical A with 4 ounces of chemical B. And again, this line is just representing the objective function with the number 195 plugged into cost, and then this 0.34 is just the location of the optimal values of x and y. Now what we can see in this example is that the edges of their feasible region, which contact our decision point, 3, 4, are both very similar in slope, and they're both almost parallel to our objective function line. This suggests a higher sensitivity, because this line, if we change the slope of this line just a little bit, we might be changing what the optimal decision is from 3, 4 to possibly this point up here, which is saying don't mix the chemicals but keep them separate, and let's dispose of a certain amount of chemical B but not A, and then this point down here is just A and not B. So this could be a way for the company to decide, do they need to mix these chemicals to dispose of them, or is it going to be better just to dispose of them separately? So just from the graphical look at this picture, there's a suggested sensitivity because of the closeness of the slopes of these edges and our objective function. However, we need to quantify those amounts. Again, we'll be looking at our model. We have our decision, 3, 4. We introduce possible changes in those objective function coefficients for their cost by introducing delta A and delta B. So these are just measuring how much those numbers 25 and 30 might change in the future. And then we just need to compare that slope to the slopes of those two edges that our solution or our decision came from. So 3, 4 was on two edges of our feasible region. So as long as the slope of our objective line is between the slopes of these two edges, we will have a picture similar to this. But once the objective line becomes either too steep or too flat, it will force us to make a different decision. So all we're going to do is take the slope of this linear function here, which again, you just solve for y. So we're going to get a negative 25 plus delta A, and then we have to divide by 30 plus delta B. And that number needs to be between the slopes of those two lines. And those two lines just come from our constraints for requirement 1 and requirement 2. If you look at the first one, solving for y, you would see a slope of negative 5 divided by 5, or negative 1. For requirement 2, if we solve for y, we get a slope of a negative 3 divided by 4. So we just put our slope of our objective function with our allowable change variables, delta A and delta B, in between those two values. And then we just say as long as delta A and delta B satisfy these inequalities, we will know that the decision of mixing 3 ounces of chemical A to 4 ounces of chemical B will still be optimal, even though it might change the actual cost of disposing of the chemicals, but it'll still be the minimal cost. So again, this first inequality is just giving us an overall relationship between the two changes, because in reality, you're not going to have just one thing changing. You'll probably have multiple costs or profits changing over time. But it's also useful to look at the individual changes. So we assume if the cost to dispose of chemical A doesn't change, which means delta A is 0, which means the cost 25 is not changing, then the cost of 30 could change by a decrease of $5 per ounce or an increase of $3 1/3 per ounce. So if delta A is 0, delta B can range within this interval of values, and we know that it will not change our decision to mix 3 ounces of chemical A and 4 ounces of chemical B to minimize our cost. Similarly, if we let delta B equal 0, we just plug in 0 for delta B in our original set of inequalities, and then we solve those inequalities for delta A. And we see that delta A can range between negative 2.5 up to 5. So again, how do we determine sensitivity? It's really based on the context and by kind of the relative size of the numbers. These numbers, negative 5, 3 1/3, negative 2.5 and 5, relative to the original cost values, 25 and 30, are much smaller than what we saw in the last example. In the last example, the profits were around $100 or $120, and the changes ranged from 80 to 200 for the different variables. So those numbers were a lot larger proportion of the original numbers. So it was not very sensitive, meaning large changes could occur and we wouldn't change our decision. In this case, any decision, a large change of delta B or a large change of delta A, meaning like of a value of, say, a half of one of these original values, will put us outside of these ranges. Therefore, it'll force us to make a different decision. And in this case, that different decision would be not to mix the chemicals and to dispose of them individually. So one thing to look at in general, if you want to basically say that a model is definitely sensitive to a variable, it's possible you'll see, generally in two variable problems you're not going to see this, but in more variable problems it is possible to see that you'll actually get one of these numbers to be 0. So if either your upper limit or lower limit is 0, that's kind of telling you that any change in that direction will cause you to change your decision, and that's very highly sensitive. So in that case, if you were to see a 0 as either of these numbers in either of these ranges, it would tell you that that variable is causing high sensitivity in the model, and therefore long-term planning is not necessarily a good idea. You want to be prepared to make changes quickly. So if you automate a bunch of things and then have to make a change, you have to re-automate everything, and that costs a lot of money. So in this case, we would say that this model, compared to the last one, is much more sensitive to changes in the objective function coefficients. But there's still some room. So again, in reality, the company would have some data over years and years of how these costs change, and they would be able to do some statistical analysis to determine how likely it will be for these numbers to be outside of these ranges, say in the next 6 months or in the next year, and therefore they could make an informed decision on whether or not they want to automate this mixing procedure or not.